TED Talk. Thanks looking for that. So Pravein is a research scientist at IBM Research Almaden, that is San Jose in the US. His research interests are areas surrounding cloud networking, multi-cloud networking, and data center networks. Uh, Prior to joining IBM, he obtained his PhD from NUS. He published several papers in top-tier conferences like SIGCOMM, NSDI, Mobicon, Census, etc. His research has been recognized with the Best Paper Award at ACM SOSR 2019, and he is also a recipient of Facebook Research Award. So we welcome Pravein, and looking forward to your talk. Thank you so much. I'll mute myself and we'll get started.
Okay. Is it okay? Okay, I can still hear myself. So. Yeah. Okay. Yeah. Just in case if you have any questions, you can unmute and ask, so that it's not. Thanks, Rinko, for the wonderful introduction. So I'm happy to talk here. So I used to work at IBM Research Bangalore. I just moved here like 6 months ago to work with UC Berkeley on multi-cloud and sky computing. So this talk, I'll be talking about application connectivity for the multi-cloud era. So I'm sure you guys would have introduction. I mean, I saw the overview of last 2 days. You've been learning about Kubernetes, application networking, and so on. So I guess I don't need to do a lot of background for this talk. So yeah, let me go in. By 2020, it's kind of predicted that cloud computing will shift from being a technology disruptor to becoming a necessary component for businesses to remain competitive. So the companies that are right now adopting cloud technology are seeing it as a capability enabler and are using its potential to have capabilities such as elasticity, rapid continuous integration and delivery, and serverless functions, and of course recently AI-infused APIs. These were not easily achievable before the cloud era. And most of the applications and businesses we interact with on a day-to-day basis are hosted in the cloud. So the rise in the cloud computing was fueled by years of innovation that was happening around abstractions for enabling the monolithic applications from being deployed to like a single server or a single mainframe machine to being spread across a heterogeneous set of machines that are actually connected by the network. So this is not an exhaustive list, but I briefly categorized it into 3 abstractions mainly. So first involving compute, which is the VMs and containers, which enabled workloads to be easily deployed in a cluster of machines on the data center. So technologies like Kubernetes are widely used now across several enterprises to have their compute deployed across different clusters and also to maximize their utilization. So additionally, abstractions such as functions as a service are being used very much for dynamic scaling of compute based on the incoming demand. And the next abstraction is the network abstractions, which enable the connectivity between the workloads that are deployed within the cluster. So typically we see virtual network overlays that are developed in the L2 layer and the L3 layer in the IP, and which span all the way to the L7 using service meshes over HTTP. Finally, storage abstractions, which enable distributed storage across systems with distributed databases like Bigtable, Spanner, and Cloud Object Storage. So these, broadly categorizing these abstractions, not necessarily are not too much simplifying it or ignoring other things, but there's a lot of other things that have happened. But just to keep it simple, I just brought these 3 abstractions, so which have hugely simplified an application developer or businesses to scale their applications elastically based on the demand, and make these deployments simplified without actually worrying about the underlying infrastructure where they are getting deployed. So if we see, you can categorize the cloud computing usage into in the 4 following ways. So one is the private cloud, where companies manage their own infrastructure. So they own the data center, the machines, and the network connectivity, and they deploy their business logic in their on-prem data center, and it's not being shared with other businesses. So this is typically a private cloud. Public cloud, where a company's whole IT infra is managed by a single cloud provider, such as AWS, Azure, or Google Cloud, or IBM. Hybrid cloud, where a combination of the two is involved, like there's a private and a public cloud being used at the same time to meet like a security, redundancy, and reliability requirements. So in some cases, companies don't want to store their sensitive data in a public cloud, so they tend to maintain it in their on-prem or private data center. And finally, multi-cloud, where multiple cloud providers are used to host their business logic or business needs of an enterprise. So in this talk, I'll be focusing on the last part, that is multi-cloud, which is kind of a recent trend in cloud computing we have seen, I think, for the last 3-4 years. This has been, this has been increasing over the period. That is, companies which want to use multiple clouds, multiple public clouds for hosting their businesses, and this is driven mainly because of various reasons, like specialized services. So there are a lot of cloud providers coming up with specialized compute services. For example, NVIDIA Cloud with GPU capabilities for AI workloads, and certain clouds offer specialized services for financial and banking services. Next is the cost, flexibility to use services at a competitive cost across different cloud providers and not get locked in to one provider, which might be expensive down the road if the cloud provider changes the costing and all that. Next is the global reach. So if the businesses want to expand beyond a certain region, they have to work with different cloud providers who offer the pertaining services for that region. This comes especially in the case where certain regions have only certain providers which provide the services at a good performance or a latency requirements and so on. Failures, which are more important, like resilience to failures. In this case, a business doesn't want to rely on a single cloud provider, because we have seen outages happening in almost every cloud provider. We don't need to pinpoint, but it happens. They need the ability to switch workloads across when a failure happens or outage is seen in a single provider or a single region. Finally, due to government regulations such as data residency laws, where businesses are required to maintain the data pertaining to the citizens of a certain country within that region. So in that case, they have to look for the cloud that is more prevalent or more available in that region within that country to serve the needs. So while multi-cloud is becoming hugely popular, multi-cloud communications, on the other hand, are still relying on multiple disjoint network islands, which are both virtualized and are legacy. We literally see, like, many of the telco providers don't change the network or infrastructure for many years, for more than a decade in some cases. So based on a recent survey, it has been pointed that one of the main barriers true multi-cloud or hybrid cloud operation is networking technology. And this is because the networking was built for a different era, like in the case like where an organization controls both the hosting of the application as well as the network connectivity. So in the sense like more like a private cloud. So however, these days in the cloud, applications can be hosted anywhere, and network flows can cross many boundaries, such as the cloud hosting providers, communication providers, and the enterprise networks. So it's definitely a time to rethink how the application connectivity can be scaled across for a multi-cloud. So if you look at this problem, the main problem with the multi-cloud application connectivity is the different perspectives involved in the stakeholders. Mainly categorized as two stakeholders. In this case, on one hand, let's say there are network infrastructure teams, the network administrators or the data center operators. So they need to keep their systems stable and reliable as possible. Like when we used to do, I used to do PhD. I used to ask the cloud admin or the network admin in my lab to give me access to certain things so that I can do something, but they wouldn't do it. So because they definitely know students or researchers will do something and make it go down. So they don't want to take any risk. So they tend to follow more rigid processes. So as a result, infrastructure networking tends to remain more static, or changes occur in a long cycle, or either goes through a long audit or various levels of permissions and all that. So this is one particular group. The other group is the teams which develop software services, such as site reliability engineers, DevOps, application developers, and so on, who want flexibility to connect different applications, move up applications here and there. So for this group, provisioning the application connectivity involves multiple teams and processes such as compliance, identity, asset protection, and so on. So if you want to connect, let's say I want to connect something, I need to raise a ticket to get a permission to enable certain things to be exposed elsewhere and connected with each other. So it's a huge asset. So unfortunately, that these two groups have different objectives, and sometimes, many times, it's contradictory. We identify two major gaps mainly in this for this application connectivity problem. So one problem is the lack of uniform abstractions. So even though like the network provides a lot of abstractions for connecting, expressing connectivity across workloads, the main problem is it is very much tightly coupled with the network configuration, such as you need to have a VPC, create a VPC, virtual public cloud, and then deploy VPN gateways and allocate the subnets to them, and configure the rules to be matching in the routing tables, security groups, and so on, and to basically create connectivity between applications that are spanning different clusters or different regions. And these abstractions are kind of very low for expressing connectivity needs, because application developers would need to have these accesses, and most often they don't get these accesses because they tell the network administrator to do these things, which are again very problematic. And finally, these abstractions are inconsistent across different clouds. So some clouds have security groups, some clouds have ACLs, and it becomes a huge learning curve for deploying across different clouds. So your application is actually cannot be ported across multiple different clouds, and in a sense, it remains logged into a single provider. The second gap is interoperability, a lack of interoperability there is. So there have been solutions to address the first problem, the lack of uniform abstractions, but what they kind of created is having a lot of different end-to-end solutions like aviatrix, Alcera, and Submariner, the first three. There are a lot of different more, but there was no space in the slide to put all of them together. But trust me, there are a lot more of such providers. So what they offer is a full-blown solutions, which are basically abstracting out the first problems, but they create another complexity by having to manage them in their own ways. They again provided as an L3 overlays, which are not compatible with each other. So either you need to be an administrator to use that in your application, which is not the case, and they do not solve connectivity across heterogeneous environments. That is, in certain cases, the last three, Cilium, Istio, Scupper, they connect end-to-end, so they connect applications that are deployed across Kubernetes. And in some cases, Cilium or Istio, they need a lot of changes to be done in their network connectivity as well. So they need to, the Kubernetes cluster needs to change their container networking itself to adopt that solution, which becomes more of an administrative level solution, which a normal user cannot do if they want to connect applications across different clusters. And more often than not, the solutions offer coarse-grained connectivity. That is, they enable connectivity across full-blown connectivity across different application groups or namespaces, which may not be necessarily be required by the user. They just want to connect one application with another. So for this problem, we kind of present the requirements which could potentially overcome these the gaps in the current solutions. So one is to allow controlled sharing of information between the workload components across the locations, which could be in different administrative domains. That is, it could be controlled by different entities, but as a user, I should be able to express what I want to share with the other user, other application that belongs to myself. Define policy on cross-domain flows. That is, the policy should be easily expressible based on the workload attributes rather than low-level constructs like IP address and subnets and so on. Allow us establishing of connections without requiring special privileges. That is, I should not necessarily be a root or an administrator to establish connections between workloads, while the administrator can govern high-level policies like whether this user is allowed to talk to the other cluster or so on, but doesn't necessarily should require controlling within my own domain. And one of the important things is ensure security on the communication, since in these cases the workloads cross different cluster boundaries, sometimes go through the public internet. Security is one of the, it needs to be secure with encryption, and avoid dependencies on specific locations, network functionality, either be it a VM or Kubernetes cluster or a Kubernetes cluster deployed by Azure or Red Hat, shouldn't ideally matter in terms of ability to connect with each other. And minimize the dependencies on infrastructural connectivity. That is, ideally, it doesn't matter which particular infrastructure or the server or the network that is being deployed by the cloud or the cluster. It should still work at a higher level than the infrastructure. And finally, we should be able to distinguish the workloads in the data plane or the workload connection. And this is mainly to to have policy on the workload attributes, and also have means to know, observe things. That is, to see what is going wrong, to see what is happening, to establish what may have went wrong, and so on. Basically, with these, the following, sorry, these requirements we came up with after surveying all these existing solutions, and working with several other teams and use cases to see what they were missing. And what we propose is, ideally, we don't need end-to-end solutions for expressing connectivity. We would need something like a building block or an abstraction for application level multi-cloud, which can be adopted by different solutions or different end users based on the use case. So we call this cluster link. And we design clustering based on the three important properties. One is programmable. That is it should be able to be, we should be able to program it. That is, express connectivity needs using simple APIs. Next is open and extensible. That is, as I mentioned earlier, it should be a building block, not an end-to-end blown solution, which has to be adopted by everyone for it to work seamlessly. So ideally, it should not be the case. I, as a user, should be able to deploy across my workloads and be able to use it, or develop other solutions on top of it. And it has to be extensible to apply to different use cases. It should be connection-oriented, ideally. L4, that is connection-oriented, as in not doing packet processing at the lower level like routers. Because what we observed is implementing that in software is very slow. I mean, it's not highly performant. Because each and every packet goes through that particular this particular piece of software, so it doesn't need to interfere in each and every packet, but ideally at a more higher level, that is the connections. So it should be able to connect like one user with other based on the TCP connection or the HTTP connection, not route packets at a lower level. So that it's also closer to application, and in that way it is easier to integrate with the application, and it's agnostic to the underlying network infrastructure. So we realize clustering as an in-cluster gateway. So in this case, this particular orange is a Kubernetes cluster. So this is an example using Kubernetes cluster, but this can be done with a VM or any other thing like a Docker and other things. For example, there's a Kubernetes cluster, then a cluster link runs as a gateway. Maybe it can run across your node or along with the application pod of the container. It can run close to the application, and it's responsible for handling the application traffic, redirecting it to the remote application that it needs to connect. The clustering basically is in the gray box. It is classified into three components based on common software-defined networking principles, like where you require to logically separate the data plane, control plane, and each of these components are individually programmed or can be replaced. For example, I need to be able to take out the data plane, replace with another data plane, and these can be individually developed based on evolve based on their own needs, and also be deployed based on they are separate deployment units, so it doesn't need to be tightly deployed within the same container or something. So they can be easily scaled up and down based on the needs. So this is the high level where Kubernetes cluster, it would just connect to an application. The data plane would process the connections, control plane would handle things like who am I connected to, this whether this clustering gateway, who are the peers to the gateway, and the policy would say whether this particular application is allowed to talk to the other application, the other cluster, and so on. So to express these connectivity needs, we define 4 entities. One is a peer, which represents a remote clustering gateway, and it would contain the necessary metadata to connect to the remote gateway, and as well as accepting connections from them. So in this example, the other cluster link, the green cluster link, is a peer of the orange cluster link cluster. The second entity is exported service, which represents an application service hosted in a local cluster and is exposed to a remote clustering gateway. An imported service next is which represents a remote application that is imported from the other gateways, which it allows to be, which is already exported by the other gateway. And finally, policy, which represents the communication rules that must be enforced on these 3 entities, like peer, exported service, and imported service. Basically, it should say who you are allowed to talk, whether this is allowed, how to load balance it, and so on. So to make it more clear, let me just illustrate with a small example. So in the previous slide, we saw just we saw mostly the components, but I'm just removing all the components and bringing it on when needed. So let's say there are 2 clusters, the orange and the green, and you have this application and a service deployed across these clusters, and you want to connect them together. So as a user, I deploy the clustering data plane and control plane, and on these 2 clusters, or within that particular namespace that I'm deployed. So the first thing I would do is to peer them, obviously, which I assume it's already done here, and then to export service A, which is done to the control plane. So when I do this, this checks the policy whether this can be exported, and then it does the export of that service. So when we do export, it doesn't do anything much in the data plane. It just stores it in the metadata that this particular service is now an exported service. So if any other cluster or a peer requests for the service, it can be exported, or it can be imported by that service. So the next thing I will do is to import the service A from the remote cluster, and again it checks the policies, and then what it does is it creates a service here, or a replica of this particular service, which is just a proxy. So this particular service is implemented as an L4 or layer 4 proxy. So now when an application connects to this, so this particular step is done one time. So for a particular service to be imported, so once it is done, this particular remote service is available in this cluster for any time to use. So when an application connects to this service A, it connects locally within this cluster, and what this does is it redirects it to the data plane of the cluster link, and then this connection gets validated by the control plane and the policy manager to see if this connection is allowed, and it goes to the other cluster's data plane, and again it gets validated by the control plane and the policy, and finally once it's allowed, the data plane, both the data planes hijack the TCP or HTTP connection, and they establish forwarding between these 2 connections. So basically it just reads the messages coming from one socket and dumps them in the other socket. That's all it does. So it doesn't need to check anything once the connection is established. And these messages are encrypted with TLS between the gateways. So yeah, this is once this connection is established, the further messages directly pass through the data plane without getting interfered by the control plane or the policy, and that this is pretty fast, I would say. Policy engine. I'll just briefly talk about this. I'm not going too deep. So traditionally, network policies are IP address based, which we don't want to go to. So instead, we base it on workload attributes like the application name, the application label, the namespace, and in some cases, the application's identity. Identity, as in there is a concept of trusted identity, where an application holds a certificate saying I am this particular application A, and I'm attested by someone that I'm actually that application A. So the policies are applied at that level and not at a lower level, and we implement basic policies like access control and load balancing, but of course we leave the policy part to be extensible. That is, we don't necessarily need to, since that's a separate component, we necessarily don't need to implement everything there. We can implement the basics, and of course, based on the use case, it will support adding other complex policies as well. So for now, we have basic things like access control and load balancing. Um, Access control is where like I have two clusters. I have three clusters, but I want to allow certain applications to connect from only certain clusters, and certain users to not connect to the other cluster, and so on. For some reason, and for load balancing, we want to have like services deployed across multiple different clusters and be able to load balance connections from one cluster to another. Where the database would be stored across different clusters, or the sum of the application logic could be handled by different clusters, and also failover, where one particular, if some cluster goes down, you should be able to failover or transfer the connections to the other cluster. So those are all basic policies we implement. In terms of implementation, we do Golang, Go-based implementation, and for data plane we use existing popular open source ones like Envoy, and we also implement a Go-based L4 proxy data plane for supporting more different or supporting custom use cases. But ideally, we should be able to plug in and plug out both of these things. And we support both Kubernetes and VM-based deployments, deploying it in a Docker or anything. And it is open source to be used. We just made it open source. In terms of performance, we just measure what is the overhead of clustering. That is how much of network performance.
Hi Pravein, just sorry to interrupt you. Do we have a lot more after this?
Sorry? Oh yeah, I'll be done in 5 minutes.
Oh, okay, yeah, sure.
Yeah, so we evaluate the performance to see how much of overhead or how much of performance bottleneck it can be, and we see that clustering with MTLS has only 10% degradation in both low bandwidth and high bandwidth servers that are deployed in GCP. And we also compare with one existing solution like Scupper, which was an end-to-end solution, and it performs very poorly because of its own choices of the data plane being different. I don't go into that. I think I've come towards the end. So basically, we are. I just presented this as an example of rethinking of application connectivity in the multi-cloud, because as more and more workloads are being deployed in multi-cloud, there's more simplification that needs to be done, and there's a lot of simplification happening in other other domains. Similarly, network connectivity also needs to be simplified in a more application centric way. So we propose certain abstractions to define connectivity with high level abstracts and a way to implement it efficiently in the network. To do that, we implement clustering in a modular way. It's available open source. And currently, we are exploring the zero trust network where we are using identities to be able to establish connectivity. And finally, we are also collaborating with Skylab in UC Berkeley. So which is basically a multi-cloud computing lab to apply clustering for their use cases, such as orchestrating workloads for multiple clusters. And there was one interesting use case that we found, like connecting serverless functions securely to perform things like multi-party computation for security. So currently MPC requires different trusted domains, and multi-cloud is like a natural separate trust domain for each cloud is a separate trust domain. So connecting these serverless functions is kind of challenging because serverless functions are ephemeral. It just comes up for a few seconds, performs some compute, and needs to transfer data, and then it has to die. So those kind of things need a lot more abstraction, not in terms of IP address and so on. So that's what we are working on right now. I think that's the end of my talk. Thanks for listening, and there are questions I would like to take.
Thanks so much, Pravein. It was really good to know about all the challenges that we are facing currently in the multi-cloud domain and the open areas where people can work on. Thank you so much. Audience, do you have questions? I do have, but I will ask maybe later, but ask the audience. Does anyone have a question? Okay, then let me quickly ask this question. So I want to ask one question that what is in it for the cloud providers here?
What is it? Sorry.
What is in it for the cloud providers so that, because we are talking about connecting these clouds and providing ease for the developers, for the users, for the end users, but how would it benefit the cloud providers? Yeah.
Okay, so Riku, can you mute it?
Yes, yes,
right.
Yeah.
Okay, good. So ideally we are not thinking about what is benefit for the cloud provider, because in this particular solution or use case, we are completely agnostic of the cloud provider. But ideally, what is beneficial for a cloud provider is if there is application portability, and a business can choose between a different cloud providers, it would hugely benefit the cloud market. May not certainly benefit the market leader, but what we are seeing is if we could potentially enable this application portability, that is application connectivity and portability across different cloud providers, it could benefit the application owners, and it's completely agnostic to the cloud provider. So the cloud provider doesn't need to do anything here. So you would see, ideally, the market would take care of it, of who is providing the specialized services. People would go towards that and all that. So that would work in itself, I would say.
Thanks so much. Thanks. That answers. Yeah, thanks. So in the interest of time, I think I'll move on to the next talk. Thanks so much, Pravein, and sorry for all the speakers. We've kept you wait for
No problem.
long. Yeah.
It happens, right?
Yeah, geographical difference. Yeah.
Mm-hmm.
Okay. I'll move on to the next invited talk.
Okay.
I think Ratul
yeah,
is
okay.
here already.
I need to go.
Yeah, sure.
Sorry. Yeah, okay. Thank you. Bye.
Thanks. Hi Ratul, I think you are already online, and are you able to share the slides? Ratul, your audio is not, we're not able to hear you if you're talking. I think you're on mute. Oh, okay, I got it. Yeah.
Oh,
Oh, I'm so sorry. Because of audio issues, I had unmuted everybody. Muted everybody. Sorry. Yeah.
no worries. Can you hear me now?
Yes. Is our audio clear?
I'm getting an echo. I don't know if you guys are.
Okay. After speaking, I'll mute my mic. So then you can check now.
Got it. Hi. Hello. Yeah, no echo now.
Okay. I'll mute myself as soon as I stop talking. Okay. I welcome Ratul. So he's our next speaker. Ratul Mahajan is an associate professor at the University of Washington and he's also co-director of UW Foci, which is Future of Cloud Infrastructure uh, group at University of Washington, and an Amazon scholar. Prior to that, he was a co-founder and CEO of Intentionet, a company that pioneered intent-based networking for network verification. And he's also a principal researcher at Microsoft Research. He got his PhD at the University of Washington and BTech at IIT Delhi, both in computer science and engineering. Ratul is a computer systems researcher with a networking focus and has worked on a broad set of topics, including network verification, connected homes, network programming, optical networks, and so on. He has published over 50 papers in top venues such as SIGCOMM, SOSP, Mobicom, CHI, and PLDI. And he has also helped develop a part of a real-world systems at Microsoft and other companies. Ratul has been recognized as an ACM Distinguished Scientist, an ACM SIGCOMM Rising Star, and a Microsoft Research Graduate Fellow. His papers have won ACM SIGCOMM Test of Time Award and the IEEE William R. Bennett Prize, and also the ACM SIGCOMM Best Paper Awards twice, and the HVC Best Paper Award. So we have Ratul with us, and he's going to talk about application-defined networking, which will connect the dots. So since we've been studying in the school about the Kubernetes networking and cloud and going towards multi-cloud, so this will be a best talk for people to understand what's beyond that and
Hello, can you hear me?
Oh, I'm sorry. Actually, I introduced you without unmuting. Can you hear me now?
I can hear you, yeah.
Okay. Yeah. So we are okay. Let's go on with the talk.
Okay. By the way, the echo is back. Okay.
Sorry, I actually introduced you without unmuting, so you couldn't hear me. Sorry for that.
I think I heard most of it.
Okay.
Yeah. And in any case, you were not saying something I don't know. So anyway, so I think thanks a lot for having me. It's a great pleasure to be here. I wish I could be there in person, but timing's odd this time of year. But either way, it's my great pleasure to come talk to you about this kind of new project we're undertaking that we're calling application-defined networking. I think the underlying observation for the work we're doing should not be kind of news to anybody. I think the observation is the following. Like if you think about modern cloud applications, how they have evolved over time. There was a time when large kind of enterprise class applications used to be built like monoliths. So you have multiple services within it. So think like eBay commerce app or large banking application and so forth. You'll have multiple functions within the app. They'll be packaged as one big bundle and then they go. But over time, what has happened is folks have learned that it's better to divide these application functionality into smaller units. So you have one service running for an independent process or a container. Running user functionality, another running payment, product, and ads. There's a lot of upside to doing that. Essentially, these individual services, known as microservices, can evolve independently. They can use different libraries. They can be deployed and scaled independently, and so forth. So this has become the way modern cloud applications get written today. And you can see that, like if you look at any kind of tier one infrastructure or cloud providers, they have thousands and thousands of these kind of microservices, and these are just microservices connection chart across 3 companies that are there. So now coming to kind of networking in us, like one major thing that has changed with this is like what used to be a function call inside these two functionalities within the same process has now become an RPC call over the network. So this was a function call before, now it's an RPC call. And this is where essentially, the world changes. The world changes because as soon as you are sending something over the network, the failure modes change. A lot of visibility goes missing as to what's going on. It becomes harder to enforce access control. You have to discover where the remote services are. And you need a lot more observability into essentially what is happening. All of this was very easy in the monolithic world, but it's very, very difficult. So the pain point was so huge that today you have like essentially tens of different frameworks that are letting you control and secure your microservices. So these things are called service meshes. And I think you may have seen some of these in your work or in general. Basically every single cloud provider has a version of it. And remember, the problem they're solving is that of connecting microservices in a secure and controllable manner. Today, more than 90% of the enterprises are using one or the other of these service meshes in there. So all this is great. So you have, you're building great applications using microservices and you get these service meshes as well. So the bad story kind of begins here. So this is a quote taken from like a distinguished engineer at Google, Kelsey Hightower. So service mesh, which is the result of spending more compute resources than your actual business logic, dynamically generating and distributing envoy proxy conflicts. So envoy here, I heard Pravein also mention that, which is basically one way of building your service meshes today across microservices and so forth. So this is pretty surprising. When I first read that code, I thought, okay, there must be some level of exaggeration there. And actually, he's not exaggerating. I'll show you some numbers later. But right before we show that, like, why is this happening? So service mesh is essentially the way they give you control over communication between microservices is by introducing this thing called a sidecar in the data path. So if you have this application service 1 here and an application service 2 there, what really happens today is that once the packet goes down into the kernel, it gets intercepted, it gets sent up the stack to a user process called the sidecar, and then it sends back down, and on the other hand, the packet gets intercepted and goes by it. So now you can see like a packet is actually taking the separatist path. The advantage of doing that is that the sidecar here can enforce any policy you want. It can log all traffic and you can do service discovery, access control, security, provide any observability. But the downside of that, as you can see, is like latencies here and CPU here. So the numbers I promised. So these are some of the measurements that we've done. There's a paper we published with this methodology. You can look up in detail to SOC this year. And what this is showing is that for two applications, this is for a single benchmark. It's showing latency overhead and CPU overhead here. So what it's showing is without Envoy, it's the dark purple line, and with Envoy, this is your light purple line. And what you can see here is that increase in latency is about 2x as well as increase in CPU. So it's very, very expensive essentially to build your service meshes today using these things. And it's not just about high overhead that I'm talking about. It's also that the sidecar that I was talking about, it's a highly complex piece of code. And as a result of that, it is not portable. So you're running this in a user process. Today, you have so much programmability in the network, so much programmability in the kernel using eBPF. None of that is available if you build your service meshes and your application networks this way. It's not just that. The sidecar today, and the final thing I say is like poor extensibility. So the sidecar today is not, it's built using standard protocols like HTTP, and this is how it does interception and does the functionalities meant to do. But the fact is, when it uses HTTP, it cannot actually talk about like application-specific constructs like, hey, I want to load balance using some field in the RPC itself that is meaningful to the application in there. So it cannot be extended into some application-specific logic that you might want. So essentially what we are asking in this project is, how can we design and implement these class of new networks, which are application networks? Before we kind of go ahead and design and think about building them, like, two things to realize here is that what you need in these application networks compared to, let's say, a network like the internet or layer 3 and layer 4 networks that we build today, you need really, really rich message processing around access control, service discovery, and load balancing and so forth. And you just don't need just IP. But we know from our networking kind of architecture classes and background is that it's very difficult to build a scalable network that has very, very rich functionality. So think about, end-to-end argument and so to speak. The saving grace for us comes to that the goal of an application network is to connect that one application, not just everyone on the planet, which was the goal of the internet. This is where I think we can actually build a network that is that can serve the needs, can be very, very rich, without actually getting onboarded in implementation complexity, so to speak. So with these two observations, we essentially proposed this thing that we're calling application-defined networking. The way to kind of understand the concept is there are two parts to it. One is that application developers will specify what they want the network to do at a high level. And they make these specifications using abstractions that are relevant to the applications, let's say in terms of RPCs and RPC fields and so forth. And because these specifications would be high level, they'd be portable. They don't specify that, hey, run it in a sidecar, or run it on a smart link, or run it before on a switch, and so forth. And then what we're going to do is we'll take a compiler and automatically generate an optimized implementation of this network. And a compiler will automatically figure out where and how the processing should happen. So I'll give an example that makes some of these concepts clearer in a second. But this is kind of the theory. Automatically, like, take the high-level specifications and automatically generate an implementation that is very, very specific to the application. So if we can do that, what we've essentially accomplished is that we can really meet application-specific needs in very, very specific ways without actually building one implementation of the network that has all the features, because that's impossible. So you can also think of this as us having cheated end-to-end argument, right? Like, which basically says you cannot have a network that has rich processing as well as scales. But we say we can scale to the application and we can have rich processing. And the secret here is an automatically generated implementation for the network functionality. All right, so how does it work? So let's say, so I'll get to the actual abstractions in a bit, but just the concept is the following. Let's say you have a high-level specification where between two services, S1 and S2, you want specific request routing. So based on a field in the RPC, you want to log the communication that is happening. You want to compress, and then you want to inject some faults to make sure that your services are robust. So think of fault injection like, just drop 1% of the RPC traffic going in as a way of introducing some chaos for testing purposes. So what a compiler does is take specifications like this, and then it can generate code corresponding to this logic here in EBPF, in P4, gRPC, or Envoy, or some other processing location. So for instance, we've got this chain of the request routing logging. One way to instantiate that would be to run these components in the kernel. So right in line, not in the sidecar. And we can decide, okay, because compression here, we can automatically know that we need to unzip here. But with the same specification, we can also now reorder the elements if we want to. The fault injection was last, but we know that we get better performance if we put fault injection here. So the rest of the elements here are doing less work because fault injection is going to drop some RPCs on the floor anyway. So why not just keep it first so you reduce your CPU usage. So these types of optimizations are not possible today, but because we have a high-level spec, we know that it's safe now to put fault injection first here. But not just that, we can do some processing in parallel as well. Why do we need to do sequentially? We can realize based on the spec of these elements that logging, compression, and request routing can happen in parallel. We also know that we can move logging from from client side to the server side, and essentially load balance, like what works happen where. And not just that, we can push some of this down to hardware. And all of this is coming from like having high level abstractions. And we can push, say, okay, if we have compression, we can do that on the smart tape as well. So doing that there might be, advantageous with respect to resource consumption and so forth. So this whole magic relies on programming abstractions. So this is work in progress, of course, and I've not settled on abstractions, but I wanted to kind of give you a taste of the kinds of thinking we are doing. So one thing was clear that, okay, we need to specify multiple elements along the way. So our abstractions are, okay, between two services, just specify the set of elements you want and specify them as a chain that you want. So very, very simple for the user to specify the chain. The interesting piece comes is like, how are the elements themselves, individual elements are specified. So for a few months, we are playing with the notion of using data flow SQL because we wanted really high level abstraction. So the idea there was that, RPC processing is kind of similar to stream processing. So why not kind of start there? One thing that we realized after trying to build it is that this particular abstraction was not expressive enough for our needs. So now what we are currently pursuing is match action style specification. So match action, you may know, it's a kind of well understood paradigm for layer 3 or layer 4 processing. It's the basis for P4 and a lot of kind of hardware oriented network processing. But all of that is today at least happens in layer 3 and 4. But the kind of processing we wanted at layer 7, where the application sits, is richer. But one thing we found in our work is that it's actually possible to express this rich layer 7 processing using some extensions that we are making to match action paradigm itself. And what we learned is that we've taken all possible onboard filters that exist today. We've taken some gRPC middleware that exists there, and what we found is that we can implement all of them in a match action paradigm. So that was a kind of nice, interesting result because as a paradigm, match action is well understood, and there's a lot of work already done on how to kind of push that down to lower levels of the stack, like in the kernel or into P4 or hardware. To kind of give you a quick flavor of what that kind of might look like, so fault injection, putting fault injection into match action paradigm, you basically do match, draw a random number between 0 and 1, and if that's less than the probability, and this match turns out to be true, I will drop it. If it's false, I'll forward it. So this is one way to kind of think about. So this is not the exact syntax you settle on, but it's a slightly high level. You just get the idea across. And then you say, okay, if you have request routing here, you can do some lookup, essentially RPC.user. So this is where like RPC specific processing that is not possible today can happen in my route table, which is user specified state. And if it's, so this is getting syntax, is getting a little Rust-like. You can say, if I find some destination D, I will essentially change the destination of the RPC to D. If I do not find RPC.user in the route table, represented by this none here, I will drop it. The key point here is that you can very, very easily specify this functionality in match action paradigm. But more importantly, now the compiler of these things has a full view of which fields are being read and written and what each RPC kind of depends on. And our compiler essentially takes this and it figures out when it is safe to reorder these elements, when it is safe to migrate these elements, all that. And these are kind of the algorithms and systems we are in the middle of it today. So just to kind of summarize, I think the work we are undertaking for application-defined networking, the starting observation is that this is basically application networks are the basis for modern cloud applications. But the way we are building them today have super high overhead and they're inflexible, that you actually cannot do application-specific things today. Like I said, make decisions based on content of the RPC without too much overhead. And the observation is that the reason we are building using sidecars and everything else is that we are trying to build something that is very, very general and can serve the needs of all applications, that we wrap it in HTTP, wrap it in TCP, and so forth. But what we're saying is that, these application networks are specific to the application itself, so why build something super general? Instead, start with a high-level spec that has the desired network functionality, and then we can auto-generate an optimized, highly application-specific implementation and bring to bear a lot of compiler optimizations that we see in programming world. We think we can bring them to networking as we generate these implementations. And with that, I'll end. I'm happy to take any questions. Thank you.
Thanks so much, Ratul, for this insightful talk. Do we have questions from the audience? Anyone? Yeah.
Thanks for the talk, Ratul. So, I was wondering that can you take some examples of this application-defined networking that could be used, like which particular set of applications could benefit from here?
Sorry, I didn't catch that question.
So, can you take some examples of this applications-defined networking? As of now, are there any deployments of that, or which sort of applications you feel would be benefited most with this application-defined networking?
Yeah, that's a good question. Sorry, I'm getting a lot of echo when that room microphone is on. Yeah. Hello? Yeah, mic. Okay, this is great. So if I understand the question correctly, I think the question is, can I talk about some applications? So actually, I think so. This is general, but like to give concretely about some applications. Let me just go back to just an example application. So this, for instance, could be, you can think of this one as your classic e-commerce website application. You've got a user database, you've got this advertising database, you've got this payment service, and you've got this product database. So what happens here is that like your front end, a user request comes in, and it's a query maybe for a product. It goes to the product database, and you might do some ad placement, and you may check is the user authenticated or not, or payment authenticated or not. A similar workflow exists for things like a hotel reservation, so to speak. Similar workflow with various microservices exists for a lot of applications. So this is essentially if you think about any application. In fact, when I was at our company called Intentional, we had built like a network verification service. That service had 11 microservices. So authenticate the user. There was a core analysis engine. There was an engine for UI. Each of these microservices. So these types of things today, they're not specific to kind of one application. This is the way cloud applications kind of get built today. What you experience as a user in your browser as one application behind the scenes is actually composed of tens or hundreds of these microservices that come together. And now folks who are building these things, their job it is to figure out kind of how to run it. And typically each of these kind of runs within a container. They figure out how to kind of run it. And the problem then arises is how do you monitor them? How do you access control across various services, because things are going over the network, and that introduces requirements that did not exist when these applications were monolithic. So your job in some sense is to kind of how to build this thing such that all the network traffic and you have these features while serving your users. Does that make sense? I'm not sure if I got the question right, but just attempt to and the answer as best as I could.
My question is like, we started with the premise that like executing all these functions. Hi Ratul, my question is that we started with the premise that executing all these functionalities in a sidecar is inefficient. So, and we tried then in your solution, we tried applying some compiler optimizations and like optimize the execution flow. So, but it's not clear like where will this compiled executable will be running in which layer? Like what's the runtime here?
Yeah. Can we switch off the room microphone? Great. So the question is, it's not clear where these things run. So this slide maybe helps. So I think we are essentially giving the responsibility to the compiler itself. So where it runs depends on what the compiler decides. So there are multiple places to run it. So first of all, we can run it in Envoy itself. Just like today, we can actually generate like a filter for Envoy itself, where some of these things may go. So this is kind of what I represented. But what's more exciting is that we can not only do that, so we can recreate today's world from this high-level spec, which has value by itself. But you still have overhead, but you at least have high levels of extensibility. But not just that, we can actually run it in the kernel. So we can translate one of these things, let's say request routing, to an eBPF program, and it can then run in the kernel. So then instead of going in the sidecar, it can go there. So, and like I was saying, like we can also then generate here the programs that run either on the SmartNIC itself or on the switch. So now, of course, like we cannot basically push into hardware any element that is doing some rich match action stuff at the application layer of layer 7. But those that we can push them down to hardware. So it is the job of the compiler to kind of figure out where to do the processing there. But because we have the spec, we know how complicated this processing is. We can decide where it should happen based on the resources that are available. And then we can generate essentially a binary implementation that goes in these various targets.
Thanks so much, Ratul. Thanks, Ratul, so much. I think people have really learned a lot about this, and I think there are multiple PhD students and MTechs here, so they would find out some path towards their research from this talk. Thanks so much.
Great. Thank you. Thanks for having me. Goodbye.
Goodbye. Yeah. I think Shahbaz is already online. So our next speaker is Shahbaz. Yeah, I think you can share your slides, Shahbaz, and test the audio once.
Hello. Hey, so can you see my screen?
Yes, your screen is visible. Yeah, thanks. I think the audio. Can you test the audio?
Yeah, I'm not hearing any echo, but can you hear me?
Yes, we can hear you.
All right, awesome. Okay.
So we have a third speaker today, Mohammed Shahbaz. Mohammad Shahbaz is a Kevin C. and Susan L. Khan New Frontiers Assistant Professor in Computer Science at Purdue University. His research focuses on the design and development of domain-specific abstractions, compilers, and architectures for emerging of architectures of emerging workloads, including machine learning, self-driving networks, serverless compute, and 5G. Shahbaz received his PhD and MA in computer science from Princeton University and BE in computer engineering from the National University of Sciences and Technology. Before joining Purdue, Shahbaz worked as a postdoc at Stanford University and a research assistant at Georgia Tech and the University of Cambridge. Shahbaz has built open source systems including PySys, SDX, and NetFPGA, NG that are widely used in industry and academia, and most of us have even read all these papers. He has received Facebook, Google, and Intel Research Award, IETF, IRTF, ANRP Prize, ACM SOSR Systems Award, APNet Best Paper Award, Best of Cal Paper Award, Internet to Innovation Award, and Outstanding Graduate Teaching Assistant Award. Thank you, Shahbaz, for joining us. It would be great talking to you. Over to you.
All right, thank you for having me. Okay, so thanks everyone for having me here. So just like what Ritu said, my name is Mohammad Shahbaz, but I'm typically known by Shahbaz. So given the context of the workshop, I thought like, okay, when we're talking about full stack networking, why not go all the way to the lowest levels of the stack and then maybe talk about what things are happening in that area, basically at the lowest level of abstraction where the hardware intersects with the software. So in this talk, I'm going to basically talk about what we are doing in the space of programmable data planes, what exists today, where we are in terms of what our systems community is doing in building these domain-specific architectures, and what kind of domain-specific hardware building blocks do we need to support the next generation of network use cases that are coming up. So the major overall topic I'm saying here, like auto-generating efficient data plane ML pipelines, but it's basically in the context of building a domain-specific set of building blocks for enabling, say, per-packet machine learning in the data plane. So let's move on. So the key thing that the way I look at networking today is basically there are two things: connectivity, so that you can connect two different devices together over the network, and then performance and security. That is, that connectivity should happen at very high speed while ensuring that the two entities are secure, the traffic is secure, and so forth. So there are two main pieces in here in networks: connectivity and performance and security. So if you look at connectivity, it's basically deterministic. What I mean by deterministic is if sender A is sending to say receiver A, then the receiver A should always receive that traffic. It should not be the case that sometimes sender A traffic ends up being at a different receiver over the network. Like the connectivity between a sending and a receiving host should always be there, regardless of what the network is doing. It should be deterministic. Because if it's not deterministic, then it can impact functionality. Like your connection will break and things will start breaking down. But if you look on the other side at performance and security, they are basically non-deterministic. What I mean by that is, well, if performance is bad, it doesn't mean that your functionality is bad. It's just that overall performance of your system is now not good enough, but the system will still work, albeit slowly, but it will still work. Similarly, if it's not secure, again, I would say like DDoS and these things are happening, so they're not impacting functionality, they are again impacting sort of like the performance of your system. So these are basically the thing that I call determinist. So in my understanding, that deterministic is something that has to happen in exactly the same way, and non-deterministic is something that only impacts sort of the surrounding performance and security aspects, but not the actual functionality of the system. So based on that distinction, what we are sort of finding out here and what we are doing in our lab is like, okay, if you look at network connectivity, purely needs to be done using routing tables and these deterministic rules that you install in the data plane. But for performance, you can actually apply machine learning here, because performance and security, the kind of thing that you want to do over there, machine learning suits pretty well over there. Today we have tons of heuristic for it because of the limitations of the data plane. But given if the data plane can do such things, machine learning will sort of be the obvious choice to apply here. So the question then comes up, if this is the case, then why are we not able to do it today? What is limiting? What is missing in today's data plane architecture or the network stack that doesn't allow us to do this like sort of machine learning based performance and security on the traffic that is coming in. And the main implication here is like you can still apply machine learning, but it's all happening in the control plane today. So basically you're installing the outcome of machine learning as rules in the switch, which again causes a lot of overhead and is not purely sort of operating at the line rate at which the traffic is coming in. So before I jump into how we can do this thing, I would actually give you a brief history of what is happening in systems and networking, because I think there's a very nice overlap here. So if you look at it, like in the 30s, we got our first fixed function processor, which is like the mainframes from IBM and other folks in the 30s. What were these fixed function processors? They were basically processors that were designed to do a certain application. They were not, you cannot program them. If you want to program them, you have to go to the vendor, tell them, okay, I need this functionality, and they will add that functionality in their mainframe, and then you go and buy it in. So this was what was happening in the 30s. And it made sense at the time because we didn't have much applications or use cases out there. So therefore, they started with this fixed function notion of a processor at that time. So 40 years forward, we got our first programmable processor in the systems community. What it did was it allowed us to now write software so that we can have high feature velocity, we can write different applications without going to the hardware vendor to sort of build a new processor with a new feature and then you start using it. So that was what happened in the 70s. But again, 40 years forward again, now what we are seeing that, okay, now we are developing domain-specific processors. So we went from pure fixed function processor design to a fully programmable processor design to now a domain-specific processor, because we are finding out that the emerging workloads like machine learning training are not a good candidate for programmable processors. They need more specialized processing, and building a corresponding domain-specific processor allows you to have a better compute per watt when running those workloads. So this is what happened in the systems community, and this is where we stand today, and there's a lot of research happening in the systems and the architecture community to develop these domain-specific processors. Now let's see what happened in networking. You know, like in the 1970s, we got our first fixed function switch. Like 40 years after the first processor, we got our first fixed function switch that was there doing routing or switching. It was fixed function developed by Cisco or Juniper, and we cannot program it. Whatever it did was baked into it. If you want to add a new feature like a VXLAN support or some new protocol, you go to the vendor will add it into the ASIC, and then you can start using it. So now what happened? 40 years forward, we got our first programmable switch. So just like we got our programmable processor in the 70s, now in the 2010s, we got our first programmable switch, which allowed us to now programmatically define packet headers, routing protocols, and things like that. So basically, networking is sort of like running 40 years behind systems, and this is where we stand today. So what this shows is like, okay, we still have 40 years further to go to get our first domain-specific switch. Because today's switch is a programmable switch. It allows you to do things that you want to do in the context of your domain, like networking. But if you want to do something like machine learning or some like network aggregation and stuff like that, or maybe off-road application-defined aspects that Ratul was talking about, well, this switch is not designed for it. It's a poor fit for those kind of workloads. So again, let's see. Like this is sort of the trend that I am seeing here, and this is what we see is happening in the networking space. So we have a long way, not that long, but still a couple of years, like sort of 10, like maybe 20 or 15 years forward. We are still not there yet. We do not have our domain-specific switch at the moment. We have a programmable switch which is good enough for the particular use cases, but we are still a long way to go to get that switch. Maybe or maybe not. So this is what I'm going to talk about, like what efforts we are doing now to get to that stage, maybe more quickly than what the TPU folks have done since the programmable processor they built. So again, looking at this again now, so programmable processors versus switches. So what's happening? So we got a CPU, we got this new workload called machine learning, and now we want to train that machine learning workload on a CPU. We found a similar thing. There's a lot of work happening in the networking community now that, hey, we can actually run machine learning on these programmable switches. So we have a programmable switch that allows us to do match action tables, and we can install these rules. So what if we can transform our machine learning workload into those set of match action rules and run them on the switch? Again, they have developed this. We have seen this. We know that they are not a good fit. We know clearly the CPU is not a good fit for machine learning, and we also know through evaluations and through the results that are coming out that programmable switch and the match action abstraction itself is not an efficient way of doing machine learning on the switches. So what happened in the systems community again? They started building their own like new domain-specific processes like TPU. They developed new abstractions, which are not Turing complete, but they are like systolic arrays on which, if you combine your machine learning workload, they can give you much better compute per watt and the density that you need for training these workloads quickly and with high throughput. But what do we have in networking? We don't have anything yet. Clearly, we want to run machine learning. We know that performance and security can get higher benefits, can improve the the performance of your network, can improve congestion, can reduce congestion, can do better load balancing, can do better security if we can somehow run machine learning on these switches. But we don't have such an architecture. And this, in the next couple of slides, I'm going to talk about the first set of developments that we have done in our lab on how to develop such an architecture and then how to develop a framework to program such an architecture. So this is the thing that we have developed. So this is the work that came out last year in ASPLOS called Taurus, a data plane ML switch. So what is happening in here is we have, if you think of the underlying data plane architecture, so basically think of the instruction set architecture of that data plane. If you remove this middle block, then what you have is a traditional programmable switch we have out there. We have a parser, we have a match action table, we have some other match action tables and the egress pipeline and a schedule. So again, if you remove this middle box, this is what a programmable switch today looks like. So what we have done is we have said, okay, match action table is a good abstraction, but it's a poor abstraction for representing machine learning workloads. But again, if you go into the architecture community, you will see they're already developing very good abstractions for representing machine learning workloads in the ASIC itself. And if you look at it at the high level, we call these abstractions MapReduce because they allow you to efficiently define dot products, hierarchy of deep neural networks, and these other like complex like arithmetic and sort of mathematical operations in a much more denser and more efficient way. So what we did was we took some inspiration from those work and we instead added a new building block in the switch called MapReduce. The way it's different from what is happening say in GPUs and TPUs is they're designed for doing batch processing. You wait for a batch of data, then you run it through that ASIC and you get high throughput and the performance that you're looking for. Well, that thing cannot happen in the switches because we cannot wait for a batch of packets and then do some processing on them. They need to be happen on a per packet basis. They need to come in, you process them and you send them out. Because if you're batching them, then you're adding delays, you're adding sort of like maybe you're causing drops. So we cannot allow that. This needs to happen at a very like on a per packet basis at very high, like fine grain and high speeds that the switches are operating at. So this architecture is more like a non-batch per packet ML block, like MapReduce block that we have added in this system. So this is sort of like the whole paper. That like if you go and read the paper, it talks about the like the internal details of how we made it possible, how we integrated the whole thing in the match action table, the programmable switch pipeline. So, but just to give you an overall description as to what is going on. So the first thing is like we developed this or we utilized this new open source language called Spatial that allows you to write these machine learning models sort of like very efficiently, but at the very lowest level. So think of it like the assembly for a CPU. So this is sort of like a language which allows you to programmatically define these different high-level machine learning workloads, and then they can get compiled very efficiently onto this MapReduce block that we have in the system. We again, for the rest of the blocks, we still rely on P4. P4 is again a language that defines how the packet should be parsed in these programmable data planes, how the match action tables should be sort of set up, so that the packets can pass through them and be matched on and acted upon by the rules that are installed in them. But for the MapReduce block, we are using a separate language that we have added in there. So the question here is like, you might ask like, okay, why not P4? But if you go and dig down into P4, you will see P4 itself is not a single language. The parser in the P4 is a separate language in itself. It's a finite state automata that you write in there to parse the packets. And then the match action tables and the control flow graph is a separate programming abstraction, which is the DAG of these match action tables sitting in there. So there are already like two languages embedded in P4. So there's a third one that we are introducing called Spatial that bakes into it and that allows you to sort of represent these workloads onto this ASIC that we're developing. So now if you zoom in here, so what happens? Basically, if you look at these programmable switches, when you come in, when a packet comes in, you parse it into something called a packet header vector. So basically, the whole byte stream is then passed into a 4 kilobit header vector where all the headers are setting, like IP headers, Ethernet header, types, and so forth. Along with that, what we do is we also add support for features that we can put in there. So the thing is, along with the generic packet headers, maybe there are some features coming in that you want to use to pass through your model. So So you can sort of store them in this packet header vector. So these features can be the headers themselves, or these features can be something that the match action tables then can encode into the packet header vector as metadata that can go through this map reduce pipeline that we have. So the rest of the headers just pass through, and then your features go into the machine learning model that is installed in here, and then you get the output, and based on that you can decide whether if it's an anomaly detection model, it can tell you whether this is a benign packet or this is an attack packet, and you can make some decisions based on that. You can either drop it exactly at that moment in the switch, or you can send it to a middle box or some monitoring sort of box sitting offshore, where they can look at the traffic and do some further processing if they have to. But this is happening on a per packet basis at the speed of the switch. That is the key benefit of this building block that we are adding into the system. So if we zoom up now, like if we look at what the map reduce abstraction looks like exactly. So a nice way to look at it is basically thinking of a deep neural network and a neuron in that network. So if you look at a particular neuron, the way you represent it basically using a map reduce abstraction. So what you do is, if you look at a neuron, what you do is the features are coming in, and then you multiply them with their corresponding weights. What does this mean? It's a map operation. So you're doing a map operation at this point. And then after that, you reduce them into a single like a scalar value, and then you feed it through an activation system like a Ratul or some other activation block that you have sitting in there. So again, this is just DNN that I'm showing you, but majority of the machine learning algorithm, even the classical ones and the new ones, they at the very lowest level, they can be represented as this map reduce sort of abstraction. And basically what it does is like, it's a hierarchy of these map reduce blocks. So, and then when you combine these different hierarchies of map reduce blocks, you can then do machine learning operations much more efficiently onto the system. And this is again exactly what is happening in GPUs and TPUs today. So there is nothing we are introducing as a new stuff. What we are saying here is like, now you need to, we are incorporating the same things, but we are running them at per packet basis rather than on a batch-based model that they have in their architecture. So the way that it runs down onto the architecture itself, so just like I showed you in the previous slide, we have these memory units and control units. So each control unit basically is made up of multiple stages and multiple lanes. So if you see, each lane can actually be something which is carrying the feature value and the weight value. Then there is a map stage. Then there is a reduction tree on stage 1 and stage 2 to do the reduction and do the Ratul operation or the activation operation onto the incoming scalar value. So this is what is happening in the architecture, in the hardware itself, which is fundamentally different from what match action tables are doing at the ASIC level or within their building blocks that they have. So now to go from this bigger machine learning model down onto this architecture, what do you do is we have augmented the P4 language. So we have the parser block from the vanilla P4, we have the match action tables in there, then we have added this new block called map reduce, which takes in the feature set and then produces an output. And using these map and reduce primitives that we have introduced in the language, we can express our model, and then the compiler will then compile it down to the particular architecture, like the map reduce block that we have on these switches. So this is basically the idea of like how we are increasing the sort of the programmability footprint of these programmable devices or the data planes that we have today in networking. So again, moving on, so the other thing is like, it's not just, the map reduce abstraction is much more general than machine learning itself. Yes, the reason why we went with machine learning is because that was our cutting edge use case that we were focusing on, but you can use map reduce to do a lot of other stuff. You can do gradient aggregation, you can do count sketches, you can even do elastic receive side scaling, a paper that we have published in AppNet on how to do like sort of receive side scaling using this map reduce building block. So just like match action tables, it's a programmable building block that you can sort of, if you are sort of maybe like you can come up with very interesting and innovative ways of using this map reduce block beyond just doing machine learning and be able to do things and processing at line rate, which was not possible before using just match action tables. So we also did, like as part of the paper, we did a full design, sort of ASIC design analysis of what it takes in terms of area and resources, like chip area and power, to build such an ASIC and to incorporate it in a sort of a traditional switch or a programmable switch that we have out there. So we calculated these numbers using a chip area of 300 millimeters squared with 4 reconfigurable pipelines, and which is basically what the today's programmable switches are based on. So based on that, based on those values, we then computed, okay, how much time does it take for a SVM model to sort of process its process a packet, and then how much chip area and power do we consume when doing such a thing. So we found that for SPM, for example, when operating at a line rate for a switch, it was only adding 68 nanoseconds of latency over on the end-to-end, like sort of doing the whole machine learning model. And the area increase was very nominal, like 6% and 1% increase in power. For larger DNN models, we found that, okay, the latency does go up, like your end-to-end latency, like the port-to-port latency becomes like 300 nanoseconds or more. But then again, the area was still nominal, 11% is not a big overhead. We have already added a lot of other kind of, logic, like Conga is sort of like an implementation for doing intelligent load balancing in the switches. Cisco has already added that. It already consumed more than 20%. So in this case, these are not like unrealistic numbers. So these are nominal. We have talked to the companies and they say like, yes, these are sort of nominal area overheads that we can expect when adding some new hardware logic in the switches. So the other thing that I want to point out is like, if this was not happening in the switch, what would have happened otherwise? You would have taken a packet, you would have marked that packet for monitoring, it would have gone to the control plane, you would have done your inference in that control plane and then installed a rule in the switch. That whole cycle would have taken around more than hundreds of milliseconds, which we have reduced down to just a couple of like hundreds of nanoseconds, which is like 2 orders of magnitude improvement on whatever you can do today when using the control plane. And all of this is happening at line rate. That was the interesting piece of this work. Okay, so now coming back to the big picture again. So we said, okay, for the systems community, we have a TPU, we have a systolic array, and we can run machine learning models much more efficiently, but we didn't have something in networking. But hopefully we think that with Taurus, we are actually taking the next step in sort of building that hardware with map-reduced abstraction, providing that sort of abstraction for running machine learning models much more efficiently onto this architecture. So basically, again, we are not saying that this is the ultimate sort of point. There's still a lot more progress that needs to be done, but sort of like we are taking some preliminary steps in that direction of enabling efficient machine learning processing onto these programmable data planes by adding these new building blocks. Okay, so let's move on now. So the thing is, well, if you look at the systems community, so systolic arrays are good, but we cannot expect a machine learning developer to write their code in CUDA, right? Or using those low-level systolic array primitives that we have. What we have is like a higher level abstraction, like these frameworks called PyTorch and Tensor, that allows a machine learning developer who has zero idea of what the architecture looks like to express their model and then compile it efficiently down to a given backend architecture. But again, we have nothing for the networking community. And also, there's an additional challenge here. In the case of systems community, we can expect that, okay, the person who is using this architecture knows how to write a model. But we cannot expect that from a network operator that, hey, he will be able to write a model using a framework like PyTorch and be able to express it. They don't even know machine learning. They're network operators. So how can we expect them to write models and also efficient models for these platforms? So this is where we have done like another work which came out in this year's ASPLOS, is like building a high-level framework that allows network operators to sort of express their intent. So we are not asking them to specify their model. We are saying, okay, give us the data set, give us your objectives, and give us the backend that you want to compile. So a backend in that case can be a Taurus block. It can also still be a match action table switch, which doesn't have Taurus. Again, we know it's inefficient, but it can still do some of these machine learning operations. Or it can be a CPU or an FPGA. So depending upon whether you're running at the SmartNIC, or you're running in a software switch, or you're running in the heart of the network using an ASIC. So what we do now is like, given these 3 high-level objectives, like dataset, dataset, objective, and target, we do a design space search for them. So we basically come up with a model for them. We do a design space search. We found out, okay, whether an SPM is a good candidate for this problem, a DNN is a good candidate for this problem, or maybe some other classical solution, like machine learning solution, is a good candidate for this problem. And after doing that design space search, we then compile it down to the particular backend. And at every stage, you can see we are giving feedback back to the user that, okay, what is going on? And then based on that, they can even put in some pragmas or give some guidance on, okay, I don't want classical machine learning model. I just wanted to come up with a DNN for this particular problem. And the compiler will then explore a design space which only looks at DNNs and doesn't look at SPMs and other things. So with that, we then compile down a efficient data plane binary that can then go and run onto onto Taurus or some other programmable data plane out there. So that was an additional challenge, because unlike machine learning, like the developers, they know how to write models. We cannot expect the network operators to do that. So we did this design space exploration for them through this framework. So in terms of the results that we found out, we found that, okay, if you look at the three baselines, and we picked these models from published papers in the past. So there was a paper that talked about an anomaly detection algorithm written as a neural network. So they were using 7 features. The number of parameters that they had was around 203, and their F1 score was 71. We found that Homunculus was actually able to come up with a better model, do a search on its own. Yes, it was able to consume a little bit more resources for this particular example, but again, we have these resources. On the switch, if you are not using these resources, you're just wasting energy. So the idea is we want to maximize the resources to be able to get a better performance. But that is not always the case. In this third example, we had a baseline model that we got from a paper which was using 30 features, and it was using like 662 parameters. But Homunculus was actually able to come up with a newer model which was using less parameters but was giving a higher F1 score. So this is what the design space exploration can help you. And it's not just like the benefits are not like, I won't say this is a new thing in our case. We are already seeing similar benefits when people are doing like sort of CAD analysis, where they're trying to map an ASIC, like a hardware onto an ASIC. And in those cases, they have seen machine learning is actually able to come up with a better ASIC design than a manual human sitting down and coming up with a particular ASIC design. So similar things are now visible here, and similar opportunities exist in the networking as well. And Homunculus is sort of like able to exploit them and come up with better models in this particular case. Okay, so now coming back to the full stack that we have for enabling ML in networking. Now we also have a framework called Homunculus, which allows network operators to now specify, okay, what kind of problem they're targeting, like anomaly detection, security, or performance. The Homunculus will come up with a corresponding model, and then the underlying Taurus compiler and the framework will then run it, and then operate it at line rate if you have to. So we sort of like again are closer to what the current full stack looks like in the systems community, but there's still a long way to go. Like this is just a initial set of work that we have done in this space. There are tons of open research challenges that I can point out. For example, Taurus, the models that you can run are very small. They are not like billions of parameter models that you can support on these switches. So we can actually take benefit from these new things coming up, like chiplet designs that can allow us to increase the size of these models. How do you handle sparsity? All the models that we have handled so far were not sparse. That's another challenge that can come up. How do you do model training at these speeds? Maybe there are newer switch abstractions other than MapReduce that are better in this case. We don't know. So there might be some more research that needs to happen in that space. And also, how do you do floating point operations? Because all of the architecture that we have developed so far is using the non-floating point operations in this case. So those are like the things that are needed on the architecture side. Similarly, on the framework side, there are still many issues. How do you do feature engineering? Maybe there are better ways in which you can do feature engineering to reduce the load on the model itself. How to do data collection? How to do labeling in this case? Because network traffic is very raw. It's not like image data set. So how do you label it? Like you cannot expect a network operator to manually sit down and label them. Again, model design itself. Maybe there are some improvements that we can think of. For example, banded models are coming up with as a new thing, which are shown to be smaller but give the same accuracy as these other large machine learning models. Again, I'm not an expert in machine learning, but talking to the machine learning experts, they sort of guide us in that direction. And then again, what kind of interfaces that we should expose to the operator, like beyond what Homunculus explored at the moment. So I hope like I was able to give you this sort of a trend that happened in the networking community and how in the systems community and how networking is catching up to it, albeit 40 years behind. But hopefully we'll get there and we'll have the same sort of paradigm and support in networking as the systems community has. So what happens now is like basically the way I see it is like we are actually in an era where we need to do co-design across 3 different disciplines: ML, network, and architecture to be able to solve these challenges that we are facing today in networking. So with that, I'll close off my talk, and I'm happy to take any questions. Please feel free to ask. Thanks.
Thanks so much, Shahbaz. You have shared your contributions towards building network processor in the data plane. I mean, thanks so much for sharing these details. It's really helpful. I will open up the stage for questions now. Is there anyone who wants to ask? Okay, in the meantime, when people decide if they want to ask a question or not, let me go ahead and ask one very maybe naive question. So you talked about per packet processing versus batch processing, right? What TPUs do today. So the question is that what would be the advantage of doing per packet processing versus batch? So one thing what I interpret is this data ingestion issue which exists for batch processing. Is that one reason, or your thoughts, please? I'll mute myself so that you're clear.
Yeah. I think that's a very good question. So basically, the thing is, your switch has, like, if you're doing batch processing, you're adding a lot of latency in the system. You need, so for example, a packet came in, and that packet was targeted for, say, doing some, it was a mice flow, it was a packet of a small flow, and now you're storing it, you're waiting on it. So that unless I get 20,000 other packets, only then I will process them and send them out. So your quality of experience end to end will become miserable. You don't want that. Like, for example, if you're watching video and doing other things, batching is not the way to go. So all the network devices that you see today, from software switches to SmartNICs to data planes, they all operate with a very strict port-to-port latency. So batching clearly breaks all that sort of constraints that we have on these devices, and therefore it cannot help in this particular scenario. So that is one particular reason why things have to happen on a per packet basis, because you do not have the luxury and you do not have the buffering available to you to sort of store the packets and then do the processing on them. In this case,
yeah. Thanks so much. Yeah, that answers. Anyone else?
Alright, cool. I think so everything is available online, so you can go and have a look.
Okay, yeah, sure. Okay, I think maybe the audience doesn't have a question. Anyone you want to? Okay, thanks so much, Shahbaz. I'm sorry for keeping you awake for so late at night.
No worries. Thank you.
Yeah, but we really enjoyed the talk. Thanks a lot. Hope to see you sometime soon. Yeah, bye.
Yes. Yeah.
So I think we can break for lunch. Sorry, break for